Hi, grade 11s. I'm going on to Newton-Raphson method today. It's chapter 30, page 121 in your books. Okay. So just to chat about a few things before we get into it. In order to use Newton-Raphson method, we've got a condition that we need to make sure that holds. Okay. So first of all, the function must be differentiable. Now, how do we know that a function is differentiable? Well, it is continuous at that point. Okay. In other words, the limit from the left of that function is equal to the limit from the right of that function. Also, the limit as x tends to a of f dash x exists. In other words, the limit as x tends to a of f dash is equal to the limit as x tends to a from the right hand side of f dashed. Okay, that is if a function is differentiable. Then we can use Newton-Raphson. So what is Newton-Raphson? Well, here's the formula for Newton-Raphson. It's xn plus 1 equals xn minus f of xn over f dashed xn. Now this formula is given on your formula sheet, so you don't have to memorize it. And now let's get into Newton-Raphson. What does it actually do? Well, it finds the x-intercepts for us, and we usually use it for very complex type of equations. And what I'm going to do first of all is I'm going to start off with a very simple equation. Okay, and what I want to do is I want to find one of the roots for this equation here. F of x is equal to x squared minus 4. So if we take f of x and set that equal to 0, what we're doing is we're finding the x-intercepts. Okay, why? Because we've made y 0. So here we get 0 is equal to x squared minus 4. Now you guys are probably thinking, well, this is really easy because all we have to do is just say x plus 2, x minus 2 equals 0, and we get that x is equal to minus 2 or x is equal to 2, and there's our two x-intercepts. And that is what I'm going to get to with Newton-Raphson. I'm going to show you how we do that. All right. Now, in order to use Newton-Raphson, we need the original function, f, and we need the derivative of the function f dashed. Okay. So all I'm going to do here with this example that we have here is I'm just going to find out what f dashed is. So f dashed of x would give us 2x. Okay, I'm going to write up the equation for Newton-Raphson. So we get xn plus 1 equals xn minus f of xn over f dashed of xn. Okay, so that's the formula for Newton-Raphson. And now what I'm going to do is I'm just going to substitute these into our function and into our derivative. So here we get xn squared minus 4 over 2xn. Okay. And what we do now, grade 11s, is we choose an initial guess. Okay, and I'll show you with further examples how we find that initial guess. For now, I'm just going to say that x is equal to 6. So that's my initial guess. Okay, I'm saying, well, that's the root of this thing. And then what Newton-Raphson will do, it'll make it work closer and closer and closer to the actual root. And what we do is we use our calculator for this. So watch how I do this. We go 6 equals. And now what that's done is it's just stored it into memory. And now I'm going to use my formula over here. So it's saying xn, which is our answer, minus the fraction button. And over here, we've got xn squared. So that's answer squared minus 4 over 2 answer. And I press equals. So that's one iteration. And we get 10 over 3. I press it again. Don't press anything else. Don't enter anything else. Just press equals. Okay, so our second iteration is 34 over 15. Third iteration, 514 over 255. once I've got my 3 iterations like this, I can just go dot, 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 and then say x is equal to. And I'm just going to go, just iterate as many times as I can on my calculator until the answer converges. Okay, and you'll see that the answer stops here once it's converged. So I just press equals, 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 and you see it's converged to 2. All right. And that's our answer. And that's what we expected over here. We expected one of our answers to be 2. All right. Now, it doesn't work out all of your x-intercepts. It just works out the one that is closest to your initial guess. Okay. So let's have a look at now a more complex type of example from your book. Okay, guys, I'm going to be working on this page over here, which is page 123. Now, some of these I'm not going to be doing because I don't want you drawing them just yet. What I want you guys to do is to do Newton-Raphson. Okay, so I'm going to start with example 2. Okay, so example 2 is saying here, check that f of x equals x minus 2 root x minus 1 has a 0 in this interval 1, 9. Okay, it goes on with other stuff, but what I want to do is I just want to discuss this first. So what it means that show that it has a 0 in this interval. All that means is we need to show that it has an x-intercept within that interval there. And how I do that is I just plug in the endpoints into my function. So f of 1 equals 1. We can just do this in our heads. So it'll give us minus 2. Okay, then f of 9, we get 3, 6 is 2. Okay, now what's happened here is you can see here that we get a negative y value and a positive y value. And what that means to us, it means that there is an x-intercept within this interval. Why? Because we're going from a negative y value up to a positive y value. Now, I'm not sure how the graph is going to go. It can go however, like something like that. The fact that it's going from a negative y value to a positive y value means that it has to cross the x-axis at some point. Okay, so now that we've got that, we now know that therefore x is an element of this interval. Okay, which means we have an x-intercept in there somewhere. Now what we need to do is we need to find this x-intercept. And what I'm going to do first is I'm going to differentiate this function because we need to find Newton-Raphson formula. So f dashed of x is going to be equal to. Now, as it stands like this is not really in a nice form that we can differentiate. So I'm just going to rewrite this for us. Okay, so there's a function that's easier to differentiate. So that'll give us 1 minus x to the minus a half. Okay, and then the derivative of a constant is 0. So there's our derivative. Okay, so Newton-Raphson's formula, xn plus 1 equals xn minus f of xn over f dashed of xn. I'm just going to plug these into our original function and into our derivative. So we get xn plus 1 is equal to xn minus xn minus 2 square root of xn minus 1. And then the derivative is going to be 1 minus xn to the minus a half. Okay. Now, with that first example, you saw that I just guessed 6, okay? With this one, however, we've got this interval 1 to 9. So my initial guess will always be the right one over here. So I'm going to say x0 equals 9, okay? So always choose the right endpoint, okay? And as you saw with the example, guys, I'm going to say 9 equals, so that's in memory now. And all I do is I just plug it into this formula over here, where if I see an xn, I'm going to replace that with aunts. Okay, so we get here aunts minus 2 root aunts minus 1 over 1 minus aunts to the power of negative a half. Sorry, negative a half. Okay, equals once, and we get 6. Two is 5,829,28564. Grade 11's notice how I write out the whole number. Okay, I will only round off my final answer to whatever they're asking us to round off to. Okay, next one. X3 is equal to 5,828,427,147. Once I've got my first 3 iterations, then I can just go mad on the equals. Okay, so here we go, equals, 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 until you can see that it's converging. And there you go. You can see that the number is not changing despite me pressing equals each time. So what it's done, it is converged. So we get X is equal to 5,828,427,125. And the question here is telling us to round this off to 6 decimal places. Okay, so X is approximately equal to 5,828,427. Okay, and that's like that, guys. Right, the next one I want to do, let's do example 3. Okay, so example 3 is a little bit different. All right, so I'm just going to read it out to you. It says find the approximate turning point of this function. So we've got this function f of x equals x to the 4 plus x squared minus 2x. Okay, so we need to find this turning point or approximate turning point of this function in the interval 0 to 1. Okay, now why this one is different is because they're asking us to find the turning point. Okay, so that is a big thing there. Now, I want you guys to remember, how do we find turning points? Well, we need to find the derivative, f dash x. And this will give us 4x cubed plus 2x minus 2. So there's our derivative. Then what do we do with the derivative? We take f dash x and we set it equal to 0 to find the turning point. Okay, and that's basically what Newton-Raphson does. Whatever function you're setting equal to 0, it can find out what that 0 is. So just like what we did here, essentially we took this function and we set it equal to 0, and we found out what x is, just like with the first example. We took f of x, set it equal to 0, and then we can find the answer. Okay, so that is what we're doing here. We're taking the derivative, and we are setting the derivative equal to 0 in order to find the turning point. Now, what happens there then is, because our formula is xn plus 1 equals xn minus f of xn over f dash xn. Remember what we did is we made the top function the original and then the bottom the derivative of that top one. Now that top one is the one that we set equal to 0. Okay, just like we did with the x-intercept. But now with this one we have to set f dashed equal to 0. So at the bottom, the derivative of f dashed would be f double dashed. So just keep that in mind, okay? Always, whatever the function's up at the top, equal to 0, regardless if it's the original function or the derivative, ask yourself, what must the derivative at the bottom be? So if we're finding x-intercepts, which is the original function, equal to 0, then the bottom needs to be f dashed. If we are finding a turning point where f dashed is equal to 0, that means the bottom we need f double dashed. Okay, right, so we'll get onto that just now. I just want to show that there is a turning point in this interval. Okay, so it's exactly the same as the previous one. I just plugged the two endpoints in. So f dashed of 0, and f dashed of 0 will give us minus 2, and then f dashed of 1. So that will give us 6, that will give us 4. And that is exactly what I wanted. I wanted going from a positive to a from a negative to a positive. That means that it cuts the x-axis between those two. So therefore, x is an element between 0 and 1. There is a turning point in there somewhere. So what I need to do now is I need to find my second derivative to plug it into Newton-Raphson. And there's our second derivative. So xn plus 1 equals xn minus, now I'm going to adapt our formula for our problem. So you remember, this is the original Newton-Raphson. So it was the top one normally that we're setting equal to 0. But which one are we setting equal to 0 now? We are setting the derivative. So this would be f dashed of xn up at the top. Then at the bottom, what did we do? We took the derivative. So this would be f double dashed of xn. Okay, so I've just adapted the formula for our problem. Right, I'm going to plug into our formulas, into our functions rather. So f dashed is over here, so we get 4 xn cubed plus 2 xn minus 2. And then our second derivative is here, and we get 12 xn squared plus 2. And our x0 is going to be 1. All right, guys, so 1 equals, now that's in memory, and it's going to be aunts minus 4 aunts cubed plus 2 aunts minus 2 over 12 aunts squared plus 2. Okay, so our first iteration is 5 over 7. The second, 843 over 1393. Then our third, and again, guys, notice how I am not rounding any of these off, only the final answer. Okay, so now I'm just going to go mad on pressing the equals and wait for it to converge. And there you go, it converged pretty quickly. You can see each time I press the equals, it's not changing. So we get x is equal to 0,5897545,123. Just want to check here. Okay, they're not giving us any decimal places. So let me round this off to 4 decimal places. So x is approximately 0,58975. Okay, so now that's the x value for your turning point, for one of the turning points. Okay, guys, and it's as easy as that. All right, guys, what you can do for me now is you can do this exercise over here. Please, with any of the ones that say sketch the graph, please just leave those, because that is the next section that we're doing, which is graphs of cubic functions, etc. Okay. All right, guys, have a good one. Thanks.